So we just have we're going to have a short overview, very short overview of complex numbers. Okay, starting with this, the imaginary number, or imaginary, the technical term is the imaginary unit. So the starting point of this business of complex numbers is the imaginary unit. So that's what I stands for imaginary. Okay, so the main purpose is, where it originates from, is the equation x squared plus 1 equal to 0, which, as we know, has no real roots. And to confirm that, you can plot it, and this is what it looks like. X squared plus y squared. I'm sorry, what I'm talking about here. Y equal x squared plus 1. Okay, x squared pulled up by 1 unit. Okay, so it cannot possibly have any x-intercepts, which, as what we just been talking about, indicates that there are no roots to this equation x squared plus 1 equal to 0. So we make it up, adding a number that is not part of real numbers. These are, by the way, as I pointed out, these are the real numbers. It is called, the x-axis is literally the real number line, so all the real numbers are there. Okay, so if we introduce something that's not there, well, that is certainly not a real number. Okay, so the point of this is it allows us to for one, as you can see, it allows us to factor our polynomial that is not factorable. If you only allow to use real numbers, it's not factorable, as we know, because that it would have had x-intercepts. It does not. But as you can see, we are able to factor it. X plus I, x minus I is our factorization. Okay, so that's how they emerge. And now what we're going to do with them is algebra to begin with. To begin with. So, so how to do algebra with I, and the answer is the same exact way. So the rules of algebra that we have known apply, and considering that this number is not a real number, anything else will not be available to us. So any kind of intuition or real life experiences with numbers will not help, because this is not a real number. Okay, so we have to actually rely on the properties of real numbers, and we just say, well, those properties now applicable to say like this, to that new number as well. So there are a bunch of properties, and one of them from the top is this one: a plus b is equal to b plus a. So that will be applicable to all numbers but n I. Okay, so but the main properties are these. So let me just characterize I in some way so that it allows us to do to the algebra with these numbers. So it's subject to all properties, all rules of algebra of real numbers. So anything you can do with real numbers, you can do with this number to begin with. But on the other hand, as the main property of where it originates, I squared is equal to 1. I'm sorry, I squared is equal to -1. So one of the operations that you can do with real numbers is to square a number. If you square I, you will get -1, which indicates I is not a real number. And in particular, it's not equal to 0. So which means that, I mean, if it's not a real number, 0 is a real number, which means that I is not 0. The good news is that you can divide by I. Okay, so this is the starting point. So these are 33 properties that you can freely apply, Okay, so let's try to do a couple of things. And so how do you add them? And the answer is same as what? As real numbers. I don't want to say real numbers, but rather analogy that probably better to bring in here is things that are not abstract numbers. Okay, so for example, if you have 3 apples plus 2 apples, what do you get? 5 apples. But you do not say 5. So 3 apples plus 2 apples is not 5. It's 5 apples. Okay, so if you skip apples, you're wrong. Okay, so similarly, if you have 3 inches plus 2 inches, the answer is 5 inches. It's not 5, it's 5 inches. Okay, so you can, apples, inches, whatever, or how about 3x plus 2x isn't 5, it is 5x. Okay, so following that lead that you've seen these before, you say that 3i plus 2i is equal to 5i. Okay, and similarly, so any kind of addition then carried out in this fashion, you can see what has happened. You can read the left-hand side as if you simply factored that thing out. You factor apples out, or you factored inches out, or x's out, or i's out. Okay, and then you carry out the operation that's left in the manner that is appropriate. So once again, 3x plus 2x is equal to 3 plus 2x, which is equal to 5x. That allows you, this algebraic, abstract kind of algebraic approach allows you to ignore the nature of x. It doesn't matter what x is. It could be, in fact, that x could be I. Okay, and it allows you not to ask the question, the inconvenient question about what is I. You can simply do algebra with it, following the rules. So if you can follow the rules and kind of push it aside for the time being and deal with numbers that you know how to handle. So you know how to handle 3 plus 2, and you push I aside by factoring it, then you end up with not having to face the question of the nature of I head on, but rather get around it. Okay, so that's the same as you deal with apples and anything of that nature. So that's addition. Addition is fairly straightforward, so it doesn't matter how many apples you have. You combine it, add them together, you have a new number of apples. Okay, so these are all called imaginary numbers. As you can see, in addition to that number I, we have a bunch of new numbers. They are all multiplied by they are all multiples of I. So once again, just like 3 apples is a multiple of apple, or 5 inches is a multiple of inch. Okay, so you multiply a certain quantity of whatever its meaning is, you multiply it by a number, and that's how you can do algebra with it. Okay, now that's addition. The multiplication isn't too bad either, but well, it is slightly harder because we don't really usually multiply apples by apples. Probably just meaningless, but the idea is the same. We got when you multiply imaginary numbers. Once again, apply the rules of algebra to try to avoid dealing with I, the nature of I. So what I do is I factor things out. 3 times 2 times I times I. Okay, so I pull similar things together, just like in the previous example. I pull the similar things together, real numbers with real numbers, imaginary with imaginary. So then I have 6, and multiply, that's the first number. What's the second number? I squared, which is? Negative 1. So the answer is, as you can see, negative 6. So that's how we do computations with imaginary numbers. The addition subtraction is very straightforward. It's as if you are dealing with some physical quantities and you don't want to ask yourself what that quantity means, you just, as long as you don't add, like feet to inches, you are fine. Okay, multiplication is slightly different, but as you can see, we just, in addition to using this idea over here that we are use all the rules of real numbers, we also once in a while will have to bring up this number. I squared is equal to -1, and as you can see, there is then a mix-up. Right away you discover that there is a way to get from imaginary numbers to from imaginary numbers to real numbers for multiplication. When you add to imaginary numbers, you can see that you're going to get another imaginary number. But if you multiply, you're going to get a real number. So when you multiply two real numbers, you also get a real number all the time. But imaginary numbers, that's what they do. You multiply, you end up with something else in nature, different in nature. Division is not hard either. 3i divided by 2i. Once again, factor things out. What's the answer?
-32.
Why negative?
I thought you divided I by -1.
No, it's when you multiply. They will cancel out. Like I said, the rules of algebra of real numbers apply. As long as I is not a 0, which is the only case when you cannot cancel numbers in that manner, is when you are facing 0. So, but I is not 0, so I can cancel, and then I end up with 3/2. Multiplication, division, and that pretty much does it. There would be no trouble for me to do division. 3i divided by 2. Okay, so I divide imaginary number by real number. No trouble. As you can see, I will simply 3/2 I. It is again an imaginary number. It's just a like multiplication I by any number. Okay, so as you can see, the four main operations of algebra are here and fairly can be carried out in a straightforward fashion. The trouble starts in the next, and so when you really realize that we cannot really keep real numbers and imaginary numbers apart. Just this example shows that they are really all intermixed. If we introduce I into the mix, then you can at any time can get real numbers. So you have to put them together, and the answer is adding apples to oranges. 3 apples plus 2 oranges. What is it equal to?
Apples and oranges.
What?
5 apples and oranges.
Well, that's a fair answer. 5 apples and oranges, okay, or 5 fruit. It's all good. The problem is if you think about why it's not working, try to reverse. Try to go in reverse. So when we say two things are equal, it means that you go from left to right and you go from right to left. But if you have 5 fruit, how do you know that they are made up of 3 apples and 2 oranges? You don't. Okay, so that's why we the answer is well, there is no answer. It is the answer itself. So we don't try to do anything we do not try to add apples to oranges, just like we don't want to mix them up without any justification. So, but it doesn't mean that there is no algebra to be made here. It is like you have 3 plus 2x, like this. So 5 plus 7x. Okay, so numbers that mix up things that may be of a very different nature. However, they could be algebra still could be carried out if you just collect similar terms. I have 3 plus 5. Plus I have 2 plus 7x. Okay, so I have, in other words, I have 8 plus 9x. So this is the kind of algebra we allow with these numbers, complicated numbers. They are complicated in the sense that they're possibly made of two objects on two numbers of different nature. The better word is complex. So these are complex numbers. Those are the numbers are sums of real and imaginary numbers. So we do not, as far as addition is concerned specifically, we do not intermix real and imaginary numbers, as we just did with apples and oranges. So 3 plus 2i is, what is it equal to? It is equal to itself. So it is 3 plus 2i, just a combination of three real number 3, and imaginary numbers 2i. Okay, so if you need to carry out any kind of algebra with more of these numbers, you can. That's not trouble. Once again, combining similar terms will give you addition of complex numbers. Okay, so what else can you do with them? You can multiply a complex number by a real number, say 2i, and then multiply it by -2. What do I get? I just apply the rules of algebra just as before. So I'll have I do the the distributive property. 3 times -2 plus 2i -2. We know that we can carry out these operations no trouble, and what the result is a new complex number. Of course, this is what this means, why I refer to this as a complex number. Specifically, it is the standard form of a complex number. It's made of real and imaginary parts, a plus bi, where both a and b are real. So in other words, it is like two numbers. The basic real number is 1. The basic imaginary number is I. Okay, so all complex numbers are made of these two. So you multiply either one of them by some number and then add them together, and that creates the standard form of a complex number, even though they might be initially in some more complicated form, and then you might be required to simplify it to find the standard form. Okay, but otherwise, even before you find it, you know that this is a complex number. Okay, and that is a complex number. You just that simplification step might be necessary in order to find the standard form to point out the real and imaginary parts. This is the real part, and this is the imaginary part. Okay, the multiplication is more complex, but still doable, because we rely once again on algebra of the rules of algebra that we do not refer to as rules of real numbers anymore, because now they also apply to complex numbers. So for example, if I'm to multiply 3 plus 2i times 1 minus I, what do I do? What do I do? I imagine that I isn't. I'm not trying to think about what I is. I'm just thinking about this in this kind of abstract way, as if this is just algebra that I've seen before, and that I just stands for something that I don't know what it is. You can imagine that it's an x. Okay, then what do I do? Well, it is factored. What's the other way around? Distribute, right. So I start multiplying. For 2 and 2, I have 4 terms. So I have 3 times 1 plus 2i times 1 plus 3 times -i plus 2i times -i. Okay? So once again, we know that once we wrote this expression, we know that the answer is a complex number. The only whatever happens afterwards is just trying to find the standard form. Okay, so I want to simplify. I have 3 plus 2i plus minus 3i, and the last one plus 2. Right? I squared is -1. Okay, so maybe I'll just more carefully write it out. 2 times minus 1. Okay. Okay, and then so the real numbers, and then I put the real with real, imaginary with imaginary. I have then 5 minus I. Okay? And that's all there is. Division is more complicated. Dividing complex numbers is slightly more complicated. You have to use some tricks of algebra to find the standard form. Just remember that all algebraic operations with complex numbers are possible. So those 4 algebraic operations, as well as any operations, functions that will come up later on, that's function, either square root of or any kind of root of imaginary numbers are also possible. And that will come up shortly, but at this time we'll just, what we have now is, this is the complex number system. Remember always that it includes the real number system inside of it. So all the real numbers, whatever you learn about the algebra of real numbers is still in there. We just added some more stuff to it. Okay, so because there are more real numbers than imaginary, there are more complex numbers than real numbers. In fact, there is a geometric interpretation of complex numbers. If these are all real, and say these are all imaginary, then every point on this plane, this is not the xy plane, this is the complex plane. Every point is represented, every point is a complex number. So for example, this one is 2 plus 3i. So you look at how many real numbers on the horizontal axis we count, say 2, and then you look at how many you've got on the vertical line, and if it is 3, then it means that the imaginary part is 3i, while the real part is 2. Okay, so you can see how many complex numbers we have. It even hard to compare, but you can see how thin the real line is in comparison to the whole plane of complex numbers. So both of them are infinite, but one is more infinite than the other, in a sense. Okay, so we're not gonna, for now, go beyond these 4 algebraic operations, and in fact 3, and just understanding the standard form of the complex number is what you need to take home from this. Okay, so the next homework probably will contain some of this. Okay, so any questions about this? Okay, so the point is kind of remains somewhat the point. The reason for complex numbers remains somewhat thin. Just remember, it helps with factoring polynomials in an extremely simple way with no exception. So x squared plus 1 is now factorable. Well, will be factorable. You have to, from now on, you have to be very careful and speak specifically whenever you are saying with real numbers, or no, I am also including complex numbers. So every time the context should be clear whether or not you are talking about all real numbers. The good news is complex numbers do not appear in calculus 1, they do not appear in calculus 2, nor they do appear in calculus 3. So not to worry. So everything remains real. The graphs that we make remains as they are. We will not try to find where that graph will intersect the x-axis. It cannot. That graph x squared plus 1, it does not intersect the x-axis because the x-axis is made of real numbers. So nothing in that respect happens. The x-axis is real, y-axis is real, and all the graphs that we have made, they will remain the same. It is when you go into more advanced parts, and then unfortunately the dimension of the whole situation increases by a factor of 2. So if you can plot the graph of a function like this on the xy plane, to plot the same function, but for complex numbers, we'll need 4 dimensions, because the input variable is complex, and that's a plane, and then the output variable is also complex, it's another plane. And so altogether, you end up with 4 dimensions. So, which means that you cannot really visualize it easily, and so, well, so it's set aside for a while. Anyway, So we are progressing from polynomials. Let me refresh your memory of what we just did about factoring polynomials. Analogously to factoring integers. Okay, so prime numbers cannot be further factored. Irreducible polynomials cannot be further factored. So that's the similarity. And every number can be represented uniquely as a factored integer, and similarly, every polynomial can be represented uniquely as factored into irreducible polynomials. The important thing over here is that there cannot be other irreducible factors other than linear and quadratic. If you are willing to deal with complex numbers, then they all will be linear. Okay, so every quadratic polynomial still can be factored, even irreducible otherwise. So this is, we would say that it is over the reals. Reals meaning the real numbers. And so most of the time you can safely assume if it's not specified, it's about reals for now. But generally keep in mind that it's possible to do algebra differently when numbers you're allowed to have complex numbers. So the fundamental theorem of arithmetic and fundamental theorem of algebra say exactly that about the factorization. The previously mentioned, where is it? It is not here. The principle of zero product principle. Where is it? So when you multiply two numbers, and they are equal to 0, then either one or both of them are zeros. So it was mentioned here somewhere. I just can't. Okay, zero factor property. This is the one. Okay. So that is why there's this correspondence between factors on one hand and x-intercepts on the other. So every factor corresponds to an x-intercept and vice versa. Because when you plug in x equal x1 over here, replace x with x1, then at least one of the factors will turn into 0, and the whole thing turns into 0, which means that you have an x-intercept. Okay, so that allows us the analysis of the function of polynomials in a way that it reveals a lot about its behavior, about its graph, from nothing but factoring. So there was a plot here at some point not a long time ago that I have factored and then had a picture. Well, anyway, so what we are moving on from here is another big analogy. In fact, we'll continue with this analogy. And that analogy is between integers and polynomials. And now moving on from integers, we'll move on to rational numbers. What is a rational number? So integers, polynomials. And now we're moving on to rational numbers. And those are simply fractions. Fractions of integers. So if you only do addition, subtraction, and multiplication of integers, you will always get a new integer. But if you divide, you're going to get a fraction. So you divide 3 by 2, and you have a number that's not an integer. Okay, so the point being, there are rational functions. So what are rational functions? If you either you know or you can guess. Rational functions are, can you guess? Well, rational numbers are fractions of integers. Rational functions are of polynomials, right? Fractions of polynomials, such as x plus 1 or x minus 1. Okay, so here I have two linear polynomials, and they just divide them. Once again, the analogy remains. So whenever you only do addition, subtraction, multiplication, two integers will produce an integer. Okay. Same with polynomials. You add, subtract, or multiply two polynomials, you'll get another polynomial. When you start dividing, you will start getting numbers that are not necessarily integers or functions that are not necessarily polynomials. So x plus 1 or x minus 1 is not a polynomial anymore. Okay, so they have also very important in mathematics. The behaviors that they exhibit are very different, and we have seen already one example is fairly prominent, is 1OX. 1OX is rational. So remember, this one looks like this. So that looks very much not like a polynomial. To begin with, the trouble starts with domains. Domains becomes an issue because we have division. Okay. Also, it causes or might cause in addition, well, it actually happens every time. Every time you have a hole in the domain. So if this is my domain, it has a hole in the middle. Okay, so whenever you have a hole, it is the function exhibits this particular behavior. As you can see, it starts to climb. A rational function, that's what it does, either climb up or climb down, and that is called such a behavior is called a vertical asymptote. So this line is a vertical asymptote. So just for the time being, it's just the language that we use to conveniently describe what we see already. Okay, so we see that, what do we see? We see the faster and faster climbing of the graph, and in fact, if you zoom in, if you rather move your window of your maybe graphics calculator, if you keep moving it to the right, to up or down, what's going to happen is they will merge. The y-axis and the graph will merge, and you won't be able to distinguish them. Okay, so that's what we call a vertical asymptote. So like this. So the graph is pretty much vertical, and it looks like, unless you zoom in more, if you zoom in more, you will see a gap. But if you don't, they will be indistinguishable. And then another property, once again, that no polynomial exhibits the same behavior, but this time on the x-axis. So if you look at it this way, it's exactly the same story is repeated on the horizontal line on the x-axis. So once again, there is no difference that you can tell from one from the other. And once again, we call this a horizontal asymptote. So this line is a horizontal asymptote. And a rational function can have it can have only one horizontal asymptote, but it can have many vertical asymptotes depending on what your domain is. So for every hole in the domain, there will be a vertical asymptote. So hypothetically, your graph might look like this. So you have a bunch of holes in the domain. So all of these are holes in the domain. Each of the holes in the domain will produce a vertical asymptote. And so the graph might look like I don't know, like this maybe, like that, like this, this maybe. Okay, so that's a typical rational function, what it looks like. While remember what the typical polynomials look like. They look like like this or like that, roughly speaking. You might have to turn it upside down. There might be a lot of x-intercepts there, but the domain is everything. The range is either everything or half, depending on the degree, either odd degree on the left, even degree on the right. So the behavior is very limited in these terms. While the rational functions, as you can see, exhibit a lot of behavior. But the idea, but still they come from polynomials, which means that the techniques that we apply to polynomials will be applicable to rational functions. And by that I mean you factor. You still factor these two polynomials, right? So, and to begin with, it's going to tell me simultaneously two things. It will tell you factoring the numerator will give me, so factors of the numerator give us what? The x-intercepts. And factors of the denominator, what do they give us? Give what? No. Look at the picture. The denominator is by what we divide. So if by what we divide turns into 0, we end up dividing by 0, right? So what does it tell you? Look at that example over here. Imagine that this x minus 1 is my denominator. So it is already its own factor. Okay, so what does it give us? X minus 1, what's the importance of x minus 1? In fact, what's the importance of 1? No. What's the importance of x equal 1 for that function? If I plug in x equal 1, what do I get? Undefined. Okay, so what is it? So what the factors of the denominator give me what? Undefined values, in other words, points outside of the domain. So these give me the holes, if you like, in the domain as well as the vertical asymptotes. So that picture on the left is, in fact, every one of these numbers. Where do they come from? They come from the denominator. All of these come from the zeros or roots of the denominator. In the meantime, to have the complete picture here, these are these. What are these? The x-intercept, and they are roots of the numerator. Okay, so as you can see, just factoring these two polynomials will give us a bunch of asymptotes, and so as you can see, the graph cannot cross those. The only way the graph can approach those vertical lines is to start climbing one way or the other. Okay, but the numerators, zeros of the numerator behaves pretty much the same way as with polynomials. They are just nothing but x-intercepts, and they behave in the same manner as, remember, the sign, the multiplicity of that root indicates whether you have crossing or you have a touching of the graph. So, for example, this one, the multiplicity is odd over here because we're crossing the x-axis. In the meantime, at the place where we're touching it over here, the multiplicity is odd. I'm sorry, even over here. So even multiplicity indicates just touching of the x-axis. Okay, so let's try one example of this is a plan, and it can be carried out very effectively if your polynomial happens to be factored. And so we're just not going to worry about how to factor it, but just start factoring. So this is my factored polynomial. Rational number is factored. Okay, so assuming that we somehow are able to factor, and then what do we do? And then it's already been factored. Each factor will correspond to a 0, so have one root. So the roots are of the denominator x equal 1, x equal negative 1. What are the roots of the numerator? What makes the numerator equal to 0?
0.
X equals 0. Anything else? The second, so x equals 0 comes from the first factor. What about the second factor? The second factor is, it is irreducible. This one is irreducible. You can guess that it is irreducible because 3x squared is always positive and 1 is always positive, which means the whole thing is always positive. It can never cross the x-axis. It can never equal to 0. Never equal to 0, so it's irreducible. So it means that there's only one to worry about, which means that 3x squared plus 1 will not contribute anything to our analysis. So I am just like last time. I will list these 3 numbers on the x-axis, and I'll mark them differently. So 0, I will put a thick point here to emphasize that is the 0. That is an actual 0, 0 of f, while these are holes in the domain. So I will put them on the x-axis, but I'll put them minus over there. I'll put them as empty holes like this. Negative 1 and 1. Okay, so at this point we could do what we did last time, and that is, so let me just summarize. So next we determine the sign of f separately on these 4 intervals. And then we'll know where it's above, where it's below, where there are asymptotes. There are 2 asymptotes, these, and we'll have a rough graph for this picture, or for this polynomial. Okay, so I'll see you next week then.